FAA presents Jim Bede, designer and builder of new types of airplanes for general aviation. His sensational bullet-shaped Bede-5 has become one of the most publicized sport airplanes ever introduced. Here on videotape, he discusses topics common to all aircraft design.
Wing design, or really the wing plan form of any airplane, this view that you see of a wing looking straight down on it, is actually a relatively important part of an aircraft design. Why? Why is wing plan form so important? Well, there are really four major factors that you can obtain with a proper wing plan form design. The four things are maximum lift, a stall pattern, roll control, and the spin characteristics. These four items can be very definitely affected by the type of wing plan form that you develop. Obviously, one objective in any aircraft design is to try to obtain the maximum lift capabilities that you possibly can out of the wing itself. For any given amount of area, the more lift you can obtain from it, the lower the landing speeds, the shorter your takeoff distance, the better overall performance of the airplane can be. The airfoil shape itself, of course, dictates what the ultimate lift coefficient could be of that particular section. But how you can use this on a real airplane depends really on the plan form, the layout of the wing itself. If you do it properly, you can end up with the maximum possible lift out of it with still very good stall characteristics. And that's the key thing. That's the item you have to have. Back in the days of the J3 Cub and so on, we had a USA 35 airfoil section on that. It was almost essentially a rectangular wing with just a little rounded wingtips on the thing. Had no twist to it, no stall strips, no spoilers, nothing else. And that airplane would be able to go to its maximum angle attack, but when it stalled rather violently and rather excessive, if you want to put it that way. But more important, the other factors, the stall pattern itself, the roll control, and the spin characteristics were a long ways from being ideal. And when anyone who learned to fly in J3 Cubs or Arancas, there was a great deal of training given to low-speed flight, approaching the airport, turning on base leg to final, and so on, just because the airplane had these characteristics. During that period of time, that was the best we knew. But since then, a great deal has been done on developing the airplane itself and preventing those kind of problems from occurring. Let's take a look at the basic wing plan form of a normal general aviation airplane. This would be a top view. We might look at a tapered wing section. This is somewhat of a standard type of design you see on an awful lot of airplanes. Fundamentally, this aircraft plan form here is quite good, except for maybe one possibility, and that is that the tapered section tends to give us a lower Reynolds number on that airfoil section, and the lower the Reynolds number, generally, the more adverse the stall pattern might be on that particular aircraft. If we would look at something other than that, say a rectangular wing plan form, well, I'll draw it down here. Where essentially we use a constant chord throughout. Johnny Thorpe was the one who sort of pointed this out to a lot of the home builders several years ago by saying that even though this is a rectangular plan form and it produces a lift distribution that isn't maybe quite as good as the tapered one or as an elliptical plan form would do, the end result is that the little bit of loss of efficiency for maximum L over D conditions is lost by a rectangular one. The advantages are very definitely better in the fact that the Reynolds number at the tip now remains the equivalent of what the Reynolds number is at the root. So one thing you know right off the bat is, without any twist in this wing or anything else, that the stall pattern of the particular wing itself will be essentially the same throughout. Now, what are the things we're really going to be looking for? Why is stall pattern so important, and what are the main objectives? Well, the ideal thing would be to have a stall pattern begin right in this region here. If we could let the stall begin here, in this portion of the wing, not necessarily right up against the fuselage, but inboard fairly close, definitely away from where the ailerons are. The factor that comes out of that is this, that if we are approaching stall and the airplane gets near its point of maximum lift and the stall begins here, the airplane will not tend to drop one wing or the other. If, on the other hand, it's outboard, and for any reason at all, you have just a little bit of yawing of the airplane or just a little bit of turbulence or whatever might occur, and one wing section, tip maybe, stalls before the other, the airplane will have a tendency to roll, and of course this can become the onset to a spin developing. So besides that aspect of it, you also would like to be able to have some roll control, lateral control, while doing this, and therefore you want to stay away from having the stall pattern begin out near the tip. If it begins at the root section in here, or inboard anyways, you will now get a nice type of buffeting. The outboard section will still fly. The airplane itself will start to pitch over a little bit, but not very violently. A little side effect to it too, if you have a standard tail configuration in the back, by getting flow separation beginning inboard like that, this turbulent air will then start to impinge upon the horizontal tail, and the pilot himself will actually get more stall warning, because he'll feel it within the stick, because the horizontal tail will sit there and start vibrating and shaking a little. This is a real good stall warning system. Without a question about it, that's a good way to do it. Now, one way of preventing the tip from stalling, sort of a method used back in the 40s and the 50s, you might say, is to put twist in the wing to reduce the angle of attack of the outboard section, called wash out. If you twist it too much the other way, it's called wash in. Nobody ever wants to do that. But you can put wash out to the wing, where you change the angle of attack, or the actual incidence of the airfoil section at the tip, by maybe 1, 2, or even 3 degrees. This very definitely has a good effect in forcing the inboard section to stall before the outboard section. Two really disadvantages of that approach. One, if this inboard section stalls at, say, 16 degrees, let's pick that just as a number, and you've put 3 degrees of twist on it, then the outboard section, if everything else would be the same, is only at 13 degrees. Well, if we take a look at the CL versus alpha plot again, this is the lift coefficient, this is the angle of attack. If this was 16 degrees, that would cause it to stall, and if this is 13 degrees right here, you can see that there is a reasonable portion of maximum CL that this outboard section isn't going to ever be able to generate. So for that amount of area and for that airfoil section, you're not getting all of the lift that you possibly can. May not be too far away from maximum, but it still is a factor, and it depends on how much twist you put on. The second disadvantage, of course, is that once you're cruising, once you're flying along, going along at high speeds, particularly for a high-speed airplane, the outboard section now may not be lifting. In fact, it could even be lifting downward. About 10, 15 years ago, there was a sailplane, a high-performance sailplane, where the designers built a little bit of washout into the wing. Now, here you are with a long aspect ratio wing, and they put this washout in it. Why, I'm not sure. I guess they really wanted a nice stall characteristic for a sailplane, but that's not really important, because you don't bring a sailplane in that landed at maximum CL. But in any event, after a competition one time, he come racing across the finish line, trying to get there as fast as he can. And as he dove through the finish line and pulled up, the outboard sections of the wings literally structurally failed downward, because the outboard section of the wing was flying at such a negative angle of attack at that high speed that it overloaded the wing spar in a downward direction. The fellow pulled up and bailed out of it. The airplane was lost completely, but he survived without any problem. But that just shows you what happens if you take a design characteristics and use it in the wrong particular place. So I'm not really very much in favor of the idea of putting washout into the wing itself like that. It can be used, but there are other things that can be done. For example, If you do something to the leading edge in here, you can immediately affect the stall. A simple way is to put a little stall strip, and I'll show you what that sort of means. I'm sure all of you have seen it, but let's take the leading edge of an airfoil over here. You can actually install a wedge-shaped device that might run 12 inches or 8 inches along the leading edge of the wing. And all this is really doing here is forcing the leading edge to stall, or to at least build up a turbulence to the point where it forces that section of the wing to stall. But there again, what you've done is reduced the maximum lift capabilities of that airfoil section within that region. So definitely, if this part could have gotten to 1.6 to begin with, it definitely cannot get that high once you put the stall strip on it. So this is a method you can be used, but I really think it's a Band-Aid. You're trying to fix something that has been done wrong in the beginning. Once you have your airplane done and you're flying and you're in flight test and you see you have a problem, it's too difficult to go back now and redesign the entire wing. That's a nice solution to it. But if you're in the early stages, when you're designing it right from the beginning, let's try and avoid using something along those lines. But what else can you do? Well, one thing can be done, and this is where Steve Whitman was very brilliant on his design of his tailwind. Take a look at a tailwind and look at the plan form. What do you see? You see a little notch here in the wing. You have the straight leading edge, and then you see a sweep back of the leading edge right as it meets the fuselage. Well, he's done it for several reasons, very cleverly. His windshield now is at a much lower slope angle, less drag on that, good visibility with it. But one of the key features that happens is that this sharp edge here causes a flow vortex to build up as the air comes around the leading edge and it got the sweep back, it rolls around, and this region in here is the region that will tend to stall. So he ends up with a real nice stall pattern, forcing it right inboard here. Now, another way of doing the thing in reverse, and you'll see this on several airplanes, where they go the opposite way. They put a swept forward portion on the wing, or the wing fillet itself. Now, this leading edge sweeping forward does the same thing. It causes the air to roll over, come over the top, and roll in here, make a vortex, and as this swirling air rolls over the wing, it actually will trigger a stall to begin in that region. It's a little bit like you have with the stall strip here, except that once you level out, once you get cruising, this swept leading edge, whether it's swept forward or backwards, has no adverse effect, whereas if you put a sharp leading edge on your airfoil section itself, that's hurting you at cruise just as well as it helps you a little bit right near your stall. So this method works very nicely, has a very decided advantage all the way around. You've seen some airplanes maybe too where they'll go to a trapezoidal section, and by that I mean to say that it's constant chord out to the thing, and then they sweep it back on the leading edge. Well, if this is done exactly right, you can develop a good stall pattern, but in many cases it isn't. It looks like it's a nice fancy little layout, it has good aesthetics to it, but if this break here is too far outboard, and if it's all the way out to where the ailerons themselves begin, then you're going to be causing a flow separation to begin quite a ways outboard, and it's always dangerous because it's not that easy to make an airplane fly through very smooth air and pull it up and stall it without any yaw whatsoever to it, and therefore to have both wings stall exactly at the same time is not that easy of a thing to do. And many times, with just a little bit of yaw to it, one section will stall first, and that means the airplane will start to roll. So something nice inboard is a good approach, trying to stay away from something outboard on the thing. Now, when we came to, say, the airplane like the Bede 5, we used a little different approach on that. We did use a tapered wing. It was a smaller chord than it was at the tip. And we're well aware of the fact that this tip now had a lower Reynolds number. And we're well aware of the fact that this airplane was going to go quite fast, so we did not want to put any twist into the wing. But we still wanted to have a good stall pattern. Well, what was the technique that we used there? Well, one of the things we did, we changed airfoil section in actual thickness. We used a 12% thick airfoil at the root. This was not very thick, but the airplane was a high-speed airplane. We did not need any thicker than that. And we went the opposite way of what the conventional thing to do. Instead of using a thin airfoil at the tip, we went to a 18% thick airfoil at the tip. But the fact that the chord was less, that the wing tapered and the chord was less, from a head-on view, And let's draw it over here. Head-on view. I'm talking from a chord line view. If you would draw the inboard airfoil section, it was like this. So this thickness in actual inches, and in this case, I think it came out to be just about 4.5 inches of thickness, which at that point equaled 12%. We drew the tip airfoil in here with its smaller chord, and it also had a maximum thickness of 4.5 inches. But this 4.5 inches equaled 18% of this shorter chord. Now what does this mean? Well, it meant that we ended up with an airfoil section outboard that had a leading edge radius in actual physical inches to be the same as it is at the root, but percentage-wise much, much bigger for the tip airfoil section. And therefore, when you have a thick airfoil section with a larger leading edge radius to it, it will give you a much higher angle of attack before reaching stall, and sometimes a much higher CL on it. So the net result was that the inboard airfoil had a lift curve slope like this, but the outboard one had one that went up like this. And this occurred about 3 degrees, let's pick 19 degrees here, about 3 degrees higher than the inboard one. So here was a situation where we had a wing design, we had it tapered, which gave us certain little advantages of being closer to elliptical lift distribution for the whole wing section itself. Yet, we were easy to construct it because we had almost the same leading edge radius. It was straight and smooth throughout. We had a equivalent thickness of the wing all the way, about 4.5 inches throughout. So therefore, in that case, when we used a tubular spar, or whether you use an I-beam spar, whatever it is, you now can have a straight spar. You don't have to bother tapering it. That has its advantages. But being a relatively thicker percentage airfoil section with a relatively larger airfoil, leading edge radius to it, we ended up with a real nice lift coefficient. Our lift coefficient went higher at the tip, and it was 3 degrees later than what the inboard section would stall. What does this mean? Well, it means that not only do we have this tapered wing section, and that we have this excellent stall pattern, which because the outboard section is going to stall 3 degrees later than the inboard section, it means that the pilot can pull the airplane up, get into a stall, have it sit there and buff it. The inboard section is going to start separating first. You're going to feel it on the tail. So you have a beautiful stall warning characteristics to it, the thing. But more important is the fact that with the ailerons in the outboard section, if the pilot happens to put in some roll control, if he deflects the aileron now downward here to lift that wing up, he is operating in this region right here. As the aileron goes down, which is like a plane flap, the outboard section will not stall just because the aileron went down. This is one of the dangers you have to worry about if you do not have a good stall pattern and if your outboard section is relatively sensitive. A J3 Cub was a good example. Here you are with the straight wing, straight sections, the old USA 35M airfoil on it, and it'd be real fine, except if you were near a stall, you still hadn't stalled yet, the airplane's flying, and then you go ahead and move the stick to the left, and the right aileron comes down. As it comes down, it tries to produce more lift out of that wing than it's capable, and that section stalls. Now what did happen? You wanted to bank to the left, so you gave left stick, but now the right wing stalls and the airplane goes the opposite direction. Immediately it confuses the pilot, and off you go, possibly into a spin. In the case of this design, we could actually sit there, be buffeting, getting this inboard section to be separating, and as we're doing that, be able to sit there and move the ailerons right and left, no problem. I'll get beautiful roll control out of it. So this meant that as you were turning from base to final, if you accidentally let the airplane get too close to stall and start getting a little buffeting and realized you had a problem and forgot good judgment and went ahead and moved the ailerons as opposed to getting out of the near stall condition, you didn't do a major mistake. The airplane itself could recover it. Now one of the other things we did on the Bede 5, some of you might remember, is that we actually used a fillet in here that had a swept forward leading edge to it. So we helped trigger off the stall by the swept leading edge, by the thicker airfoil out at the tip, and the end result is you can have an extremely good flying airplane. One side effect of all of this is how does the airplane act in a spin? I mean, first we're talking about stall patterns, but then what happens once you really get into a spin? Well, most of the time the same thing that gives you good stall characteristics and good stall patterns will be the same things that will give you good spinning characteristics also. Good spin characteristics, of course, are very important for any airplane. Whether you've designed it to be an aerobatic airplane and you want to be able to demonstrate it that it can actually spin, or if it's just a straight general aviation or a home-built aircraft that you want for normal flying, it's very advisable and wise to have one that has a nice spin characteristic so that if you purposely or accidentally get into the spin, it will also recover quite well. There are several things that you can do to influence this. NASA has been doing a fair amount of work recently in wing layouts. Let's in this case look at a more rectangular type of planform. And they have found that if this outer half, at least the outer 1/3, is handled significantly in preventing that portion from stalling, whatever the method you want to use. And one of the things they did, they put a cuff on here which with a very large leading edge and actually drooped. And of course what that was doing is preventing the stall from occurring in the outboard section to quite a bit after what it would do in the inboard section. When they did this, they found that the airplane was almost unspinnable. It could have excellent characteristics. In some cases, you just could never spin it, or if it did spin, it was very easily to recover from it right away. And one of the reasons was that this portion of the wing itself was not stalling, was not separated, or was considerably less separation once it got into a full spin as compared to the inboard section. How this is done is you got to watch very carefully. If you're not concerned about the cruising condition of the airplane, all right, then you can put these big cuffs or big leading edge radiuses to it, which will give you the good low speed characteristics, but one of the disadvantages is it does create a fair amount of drag once you're cruising along. Another way is to put a slot on there. I think most of you are familiar with what a slot would look like. You can actually literally cut the inboard section out and put a gap or a slot in the leading edge. There are a number of reports out, incidentally, on how to do this. You don't just arbitrarily take a wing airfoil and cut an opening in the thing and let air come through it. That doesn't quite do it. But a properly designed slot will give a very definite effect, primarily in the fact that it will take, go back to the old famous lift curve slope, your CL here versus alpha. What it really does is take the original curve and just keep extending it on up, sometimes as much as 5, 6, 7 degrees. Now that's an excessive amount in one way, but excellent from the standpoint of aileron control and stall control, because this slot allowing the wing to go to much, much higher angles of attack before it separates is extremely good. The problem with the fixed slot is that it just about doubles the drag of that airfoil section. It's a very significant increase in drag. If it's a type like flying a heliocarrier that rolls in and out, then you have a nice fact in the fact that when it's closed, you do not have any more drag than the standard airfoil would be. When it's open and at high angles of attack, you now have the high lift characteristics. The disadvantage, of course, is that you have to make more parts, more mechanism, and design it just properly. But when you look at any of the airlines, the jet airlines and car, they all have some form of leading edge treatment to it because it's an important thing. It can and will enhance the lifting capabilities of the wing quite a bit. But a fixed slot or a movable slot out here in the outboard section will give you that stall pattern and that spin characteristics that you're looking for. It will do a good job to it. There are some other sort of subtle things you have to watch out for. When Dr. Raspet down in Mississippi State was doing a lot of work on a Cessna L-19, they start using boundary layer control, suction boundary layer control, blowing boundary layer control. And one of the things they found that occurred that was sort of strange was that if you have your wing like this, and if you have really good, powerful flaps built into it, to where you will be pulling in a great deal of air over the wing and producing real high CLs, that your stagnation point, the point where the air comes along, hits the wing, and one side of this point, the air goes around the leading edge, and in the other case, it goes under the wing. Where this stagnation point is something you have to be aware of. I'm sure you all remember the simple little stall warning device, which was just a little tab connected to a micro switch that would stick out there. And as the airplane's nose came up and the stagnation point moved behind and underneath that little tab, it pushed the tab up, which activated the switch, which gave the pilot a warning that he was getting near stall. And it worked quite effectively. Well, on the L-19, what happened is you have a strut coming down at a certain portion out in the wing, and they produced so much lift with the boundary control that the stagnation point actually came and it touched the wing at where the strut meets the bottom of the wing. And someday if you get a chance to look at an L-19 or even a Cessna 172 or something like that and see where the strut comes in underneath there, it's amazing how far back that stagnation point would come, touch the wing, and then the air would rush forward underneath the wing all the way around the leading edge and up over the top. But as soon as it got to the strut area, in that one region where the strut met the wing, it actually would separate here and cause turbulence and cause the wing to start stalling in that section of the planform where the strut would meet the bottom of the wing. So when you're working on this type of stuff and doing design, be careful what you have down underneath there. Don't have a situation where you got skin and a big gap underneath there or some really heavy rivets or something like that. Even though it looks like it's under the wing and reasonably far back, it still might be a factor at high angles of attack and actually kicking off your stall pattern on here. Incidentally, Dr. Raspa did a nice study on this one time. When you're generating a lot of lift on the wing and that air is rolling around the leading edge of the wing, it actually is pulling 6,000 Gs. Now the molecules don't weigh very much, but still they pull 6,000 Gs in centrifugal force in going around the leading edge of the wing. So you can imagine the kind of energies that are involved in the airflow as it flies over a particular wing. The planform of a wing, as I said before, can affect four major things. The maximum lift of the wing, and that's what you want to do. You want to get the maximum lift you can out of it. It can affect the stall pattern. Your airfoil is important, but even if you have a very bad airfoil section, and to me, a very poor airfoil section is that old 230 12 or 15% thick airfoil, the 230 series. They have such a bad stall characteristic, and yet it's used on the DC-3 and it's used on the Bonanza and an awful lot of the Beech airplanes. But by planform alone and by leading edge treatment and everything else and twisting of the wing and all that, they still can get a reasonably decent stall pattern out of it. However, if you have a good airfoil section, an airfoil section that has a good stall pattern by itself alone, and you go ahead and use a good planform layout for the thing, your end result will be that you'll have a spectacular flying airplane with excellent stall characteristics to it. And these excellent stall characteristics then gives you the third thing, which is roll control. You'd like to be able to sit there and be able to move the wheel or the stick and roll the airplane under any condition. High speed, cruise, normal cruise, low speed, right up into stall. There's nothing wrong with having an airplane that will sit there and be stalling and vibrating and shaking, and you still can sit there and move the stick back and forth and roll the airplane from right to left. Back in the days of the J3 Cubs, of those of you who learned to fly, one of the most critical thing was for the instructor to teach you, as you got the nose up, as the airplane got slower, you never move the aileron. You start steering and holding the wing up or down by using the rudder itself. And what did this mean? It mean a person had to learn to fly an airplane so that when you're coming in on downwind leg, for example, and you wanted to bank or do anything, you use the stick and the rudder. As you turn base, you still can use the stick and the rudder, but as you slow down and turn from base to final and got real slow, and the wing would start to rise or fall on you depending upon the gust conditions, you had to start remembering, no more ailerons, just using rudder alone. Well, that's unfortunate because if something happens real quick and your reactions take over rather than thinking about it, you may tend to use an aileron, and if the wing is designed improperly, using that ailerons will get you more into trouble as opposed to getting you out of trouble. So today's technology does allow us to design the wings right so we can have roll control right on into the stall, do it right, and have it the proper way. Once you've got that, once you've got a good stall pattern, once you've got roll control, your chances of having good spin characteristics are greatly, greatly enhanced. There are a number of reference materials that you could look at. However, there are two NASA reports that are pretty good. One is Technical Report 829. That is entitled Summary of Measurements in Langley Full-Scale Tunnel of Maximum Lift Coefficient and Stalling Characteristics of Airplanes. This report shows a pretty good comprehensive analysis of existing airplanes of that time and what their stall characteristics were and maximum lift capabilities. It deals primarily with plan form and shapes of leading edge and various factors that enter into influence in the stall pattern. A second report that is good is Technical Report 868, and that it's entitled Summary of Lateral Control Research. This basically talks about the ailerons, spoilers, and various other factors that you use for roll control, but it falls right into the same category of what do you do for the planform and how do you lay it out. I'm not sure if these TRs are available through the government agencies anymore. Some of these are out of print, but you can write to the proper agency to get that. However, we will be making available copies, Xerox copies, reprints of these TR reports, and they can be obtained at our facility with a complete catalog that gives you also the prices of what the other reports would be. Here's a model of a T-18 home built. It's a very well designed aircraft by John Thorpe, quite popular, but it has a number of features on it that might demonstrate a little bit what we've been talking about. For example, it has a straight chord wing, essentially a rectangular wing planform, straight leading edge. It does have polyhedral to the extent that the inboard section has no dihedral and the outboard section does. Now right here, where there's a break in the dihedral, there also becomes a slight break in the leading edge itself. So this region right here will probably be an area where the stall pattern will start to begin. You can, of course, put a stall strip on the leading edge inboard if you want to, but in this particular case, the stall pattern will probably generate about the middle of the wing. It isn't ideal from the standpoint of the stall pattern. You maybe would like a little bit further inboard, but it's really not too bad either because there still is a generous portion of the outboard wing that will be working. This sort of represents a normal design compromise you want to do. John Thorpe has a constant chord wing. The Reynolds numbers at the tip is the same as at the inboard section, so that's quite good. But he does have this break in here, which from a stall pattern standpoint isn't ideal, but from a structure standpoint was quite good. What he has here is a inboard section of the wing that he could make as a one-piece spar going all the way through the wing. And the first set of joints on a spar isn't until you get to the break in the wing itself, and that's when the spar can go down to be thinner and lighter and so on. And that's really a pretty clever approach he has, because a lot of times the designer will have the break on the inboard section of the wing close to the fuselage in this region in here, but that also happens to be where the highest stress concentrations would be because the loads are the highest on the spar right inboard like that. So in this case he probably saved some weight and made it a much simpler design by making it a one-piece spar with the brakes in the outboard portion of the thing. I'm not sure really on the T-18 whether he has any twist in the wing. He may have 1 or 2 degrees of washout on it that would assist in giving the proper stall pattern all the way around. But it does represent a typical home built, and it does represent a good design, and one again where you do have to compromise. What you'd like to get in one aspect of the thing may be structurally or cost-wise more difficult to make, so you balance that out with the overall design of the airplane.